After watching this video lecture, students will be able to define enthalpy and its relationship to heat under constant pressure conditions, identify specific chemical reactions as exo or endothermic, and calculate the enthalpy or heat values for reactions given specific data sets. So enthalpy, which is represented by the letter H, is a combination of the state functions energy, pressure, and volume. And enthalpy can be represented by this equation here. So enthalpy is equal to the internal energy plus the product of pressure and volume. Okay, so if we want to look at the change in enthalpy, which is something that we'll be observing and analyzing very frequently in chemistry, we're going to go ahead and utilize this equation here. So change in enthalpy is equal to the change in internal energy plus the change in our product of our pressure and volume. Okay, now so since energy, pressure, and volume are all state functions, enthalpy by default is also a state function. Okay, so now we're going to be looking at enthalpy with respect to two conditions. We're going to be looking at constant pressure and constant volume conditions. Okay, and so let's go ahead and let's see how enthalpy is related to our variable Q, or the heat, in the various conditions that we've discussed. Okay, so let's go ahead and bring this back to our change in internal energy equation. Okay, and we're also going to look at our work being only pressure and volume allowed. So we're going to look at the relationship that we see here. Okay, so let's go ahead and let's plug in our work variable and go ahead and substitute that pressure volume work variable. Let's go ahead and solve for Q. Okay, so we end up with the following equation. We go ahead and we look at this equation and what Q is equal to. It actually shows up and is exactly the same as what our enthalpy value is. Now remember, this is at constant pressure. Okay, so really this delta value only applies to our delta V, or our volume variable. Okay, so we end up with what delta H is equal to being exactly the same as what Q is equal to. So at constant pressure, okay, our delta H, our enthalpy change, is going to be equal to our heat. And so this is a very useful relationship when you're dealing with constant pressure conditions. And in chemistry, basically, probably 99% of the chem that you do is going to be at constant pressure conditions. So this relationship between enthalpy and your heat transfer, or your heat that is either absorbed or released by your reaction, they are going to be equal to one another. So if we go ahead and we take a look at constant volume conditions, if we were to go ahead and once again utilize our equations that we see up here, we would get that Q is equal to delta E plus P times delta V. Okay, now in this situation, constant volume conditions, basically the volume of your container is not going to be being altered through the process. What that means is that I have no change in V. So change in V in this constant volume condition is going to be equal to 0. Okay, so if we go ahead and we take that 0 value for our change in V, okay, and we plug it in, what that ends up doing is basically canceling out our pressure volume work variable. Okay, so and that leaves us with delta E being equal to Q. Okay, so in constant pressure conditions, or excuse me, constant volume conditions, Q is going to be equal to delta E, not delta H. So the reality of it is this type of relationship doesn't come up very often. We'll see in the future the concept of bomb calorimetry. Bomb calorimetry is when this relationship is going to be utilized, and when I mention it, you'll already know why. Okay, and at constant pressure conditions, enthalpy is related to Q as such. Now, one of the main reasons why we want to relate our energy changes and such to Q is because Q is a very easily measurable variable in chemical reactions, and we will see that when we have our calorimetry discussion. So for chemical reactions, the delta H, or the change in enthalpy, is going to be directly related to the difference between the enthalpy of your products and your reactants. So in a situation where your enthalpy of your products is greater than the enthalpy of your reactants, you're going to have a delta H that's going to have a positive value. Conversely, if you have products that have a smaller enthalpy than the reactants, you're going to end up with a negative delta H value, or negative change in enthalpy. Okay, so this directly corresponds to constant pressure situations, in the sense that at constant pressure, so pretty much any type of reaction you're going to be carrying out in most chemistry classes, your delta H, remember, is going to correspond directly to Q. Okay, so a negative delta H is therefore going to give you an exothermic process. A positive delta H is going to give you an endothermic process. Okay, so this generic equation relates your products and reactants to give you your overall change in enthalpy. Now, the delta H value that we just discussed brings us to a more specific situation when we're referring to the delta H of the reaction, or RxN, as you're seeing here. Okay, the delta H of your reaction, or your enthalpy of your reaction, is an enthalpy change that accompanies a specific reaction. Okay, and these specific reactions are represented by thermochemical equations. These equations are specific balanced chemical equations that show a specific enthalpy change for specific molar amounts. Okay, so if we look at this equation right here, basically we have the combustion of methane into gaseous CO2 and liquid water. And the enthalpy change associated with that process is seen here. Okay, so we can derive a lot of information from this specific reaction. Okay, we know that this is an exothermic reaction because of the negative sign. We know the quantity of energy that has been released because we've been provided with a numerical value with units. Okay, and what you need to understand about these thermochemical equations is that they are directly related to the quantities that are present here, as well as the specific states of matter and the direction of the reaction that's being carried out. So if we were to look at this equation, the way we could describe the enthalpy value is that for every 1 mole of methane, you produce, or this reaction, this thermochemical equation, would produce negative 890.4 kilojoules. Okay, now if we were to adjust this reaction, increase the quantities or decrease the quantities, this enthalpy value would change correspondingly. And we'll discuss that in more detail a little later. Now, what I want you guys to understand about this equation up here is that we will be coming back to it and using it in very specific ways. But for right now, we're just looking at this in a generic sense, in that the products and reactants differences are what are creating, or what is providing us this delta H value. So we're going to go ahead and look at these practice problems. So when magnesium metal reacts with oxygen, 1,204 kilojoules of heat are released. We're going to use the balance equation that's been provided below to answer each of the questions. So in A, they want us to calculate the amount of heat released when 2.4 grams of magnesium reacts with oxygen in the air. Okay, so what we're going to do is we're going to go ahead and we're going to look at the relationship here between our magnesium and our enthalpy value. Okay, so we know that negative 1,204 kilojoules are released for every 2 moles of magnesium. So what we're going to do is we're going to convert our grams of magnesium into moles, and then we're going to use the relationship that we have here to figure out the quantity of heat that's produced when this reaction occurs. So if we go ahead and we look at this problem, we have converted from our grams of magnesium to moles of magnesium, and then we use the inner relationship between our moles of magnesium and our enthalpy value here to get into our quantity of heat that's going to be released. So if we go ahead and plug this in our calculator, we end up with negative 59.45 kilojoules, okay, which would be negative 59 kilojoules of heat that is being released. Now normally, guys, what I want you to understand is that there's really no such thing as a negative heat value. The negative sign that you see here is indicating whether or not the heat is being released or absorbed by the system. So really this answer is going to be most correct when we just say 59 kilojoules of heat is released. Okay, so I need you guys to understand that there's no such thing as a negative quantity of heat. That's just an indicator of the directionality of the heat transfer relative to the system. Okay, so now that we've looked at the relationship between our quantity of heat and the mass of a substance that can possibly be used to produce products, we're going to go ahead and look at how we can relate our heat values from a specific system to figure out how much mass of a product is produced in the reaction. Okay, so in this case, what we've been told is that we have released negative 96 kilojoules of heat during the process, and we want to know how much magnesium oxide is being produced during that process. So what we're going to go ahead and do is once again use the relationship between our enthalpy value and our balanced chemical equation to figure out how to convert this quantity, or this known quantity, into our moles and subsequently grams of MgO. Okay, so we're going to go ahead and set that up. So now that we have this set up, we have our kilojoules of heat that have been released from the process that we're analyzing. We have the relationship from the balanced equation and our enthalpy value. That multiplication here is going to allow us to get into moles of MgO, and then we're going to use our molar mass of MgO to get into grams of MgO produced. Okay, so we're going to go ahead and plug this into our calculator, and that is going to give us 6.4 grams of MgO produced in this reaction process. So the interplay between the balanced equation and the quantity of energy or heat that's going to be released or absorbed by the process is going to be directly correlated to the mole amounts. Those mole amounts can be directly correlated to mass amounts of reactants or products. So make sure that you guys are comfortable with that interplay, and that'll allow you to calculate problems such as these. Additionally, guys, please remember that the sign of your enthalpy value is always going to indicate the direction of the heat flow, but remember that there isn't any such thing as a negative heat value.